Good. So good morning, everyone. My name is Louise Kellogg, and so I wasn't here last week. It's nice to see all my old friends and meet all the new people here. So I've been asked to talk about, I want to give the fourth Geodynamics lecture, and that's about mixing. And so you've already heard about the governing equations for flow in the mantle, and which is where we're going to focus our attention. We're going to focus our attention today on the mantle. You've heard about flow in the mantle. You've seen the governing equations. You've seen subduction. You've seen some geochemistry, which has told you a little bit about some of the processes that create heterogeneity in the mantle. And you've seen seismic data that tells you something about the scales of heterogeneity in the mantle. And so what we're going to focus on today is the process by which mantle convection and flows in general tend to destroy heterogeneity. And so it turns out that, the mantle itself, by its processes of melting and extraction of melt, all the processes that cause differentiation create heterogeneity. Those are introduced back into the mantle by subduction, possibly by processes at the core mantle boundary, but convection in the mantle tends to circulate them and tends to destroy those. And so there's a balance between the time scales and the length scales for production and destruction of heterogeneity. We're going to focus today on the destruction of heterogeneity. And so that's basically what we're going to talk about. Now, as you can imagine, mixing is a process that doesn't just apply to the Earth, but also applies to a lot of other processes, including engineering processes. So there is a vast literature about mixing that comes primarily from the engineering literature. And so that means we don't have to reinvent everything. We can basically draw on that. And so a few times here I'm going to draw on that. This picture is from a classic book by Otino, who is really one of the founders of this field of study on the kinematics of mixing. And what you're looking at here is a kind of a simple, conceptually simple model in which he has a tank of fluid and it's a bluish, and then he's injected some dye, this green dye on this end and this red dye on this end, and then he's driving the flow by motion, by shearing motion back and forth with a plate along the top. And that is leading to a very complex flow, but you can see that over time it leads to extremely odd mixing behavior, right? So this green blob, this red blob started out as the same size blob, but the red blob is being sheared and folded and stretched. The green blob is pretty much remaining unmixed. And so this is often going to be the paradox of mixing, is that it's quite sensitive to what the flow, the specifics of the flow is. And since we don't know the specifics of the flow or the history of the flow very well in the mantle, that makes it a challenge.
Continuous injection of the red?
No. There's one red.
There's not conservation of redness.
There is. It's just been, there's not conservation of redness because basically it's stretched. And that's just sort of diffused out. You'll see that in a later slide as well. There is conservation of the red material. It's just that it looks like there's more because it's been stretched so much. Yeah. Actually, I'm glad you asked that. Yeah, I know. Wow is right. It's pretty cool. So let's, this is a very brief outline of what we're going to do. First, we're going to think about why we want to think about mixing, or why we would want to model it in particular. Then I'm going to talk a little bit about the mechanics of mixing. This is a vast subject, and so I'm going to leave a lot out. But I'm going to talk a little bit about the mechanics of it, and then try and apply that a little bit to mantle mixing. Again, this is a vast subject, so I've left out more than I'm including, but I'm trying to give you a sense of what the main interesting topics are. There's a lot of thought that goes into how to quantify mixing and how to visualize it, and especially when we get into 3D flows. So most of the models I'll show you are 2D, not because we can't do 3D, but because 3D is hard to show. And then we'll summarize with some key points, which I will basically start with in case we don't get to them again. Okay, so I already said this last point, which is that mantle processes create heterogeneity, largely by mixing and differentiation, and also destroy heterogeneity by mixing. And so these are the points I want to make about mixing itself. So stirring, and we'll get into the distinction in a minute between stirring and mixing. Stirring is controlled by basically stretching and folding. So you can think of this in terms of various kitchen analogies, but you can think of it in terms of what happens when, if you've ever seen saltwater taffy made, there's a machine that pulls it and stretches it, pulls it, folds it, pulls it, folds it, and that mixes in the flavoring and it mixes in the dye, which makes it whatever color it ends up with. And so that stretching and folding is actually key to mixing in engineering applications and also in the mantle. And that stretching and folding creates a kind of cascade of scales of heterogeneity, which is going to be important to us. We're going to look at a few things, but one of the things we're not going to look at is turbulent mixing. It doesn't apply to the mantle. It would apply to the core and to some magmatic processes. But the type of flow makes a big difference to the style of mixing. And there's also a big difference between 2D and 3D. And then we'll talk a little bit about how the scale of interest is going to influence what we conclude about mixing. Okay, so let's start by why do we care about this problem? Some of these figures may have appeared already in talks that you've seen. If we look at basically the most of the basalts that are coming out of the mantle, mid-ocean ridge basalts, and we take some of the main tracers that we use, in this case helium-3, helium-4, which is a measure of how outgassed the mantle may be, you'll find that the bulk of basalts coming out at mid-ocean ridges fall in a very narrow range of helium-3, helium-4 ratio. And so that implies that and various other measures like this imply that the mantle source of morb is well mixed. And since we think that the mid-ocean ridges are, in some sense, can be thought of as randomly sampling the upper mantle, that means that the upper mantle can largely be thought of as pretty well mixed. So that's an observation that any successful model of mantle dynamics has to produce, or it's inconsistent with observations. On the other hand, if we look at the ocean island basalts, which are a much smaller volume, but quite interesting, we find a much wider spread of heterogeneity. And so that wide spread also implies that the mantle is not well mixed, or at least some portions of it are not well mixed, that the mantle as a whole is not entirely homogeneous. And so any successful model of mantle convection has to predict that as well. So that's really going to be fundamental to this, and there are a variety of ways to express this as well, a variety of observations that express this. If we look at a fine scale, we see a certain amount of heterogeneity as well. This is a paper from 1993 from the Galapagos Islands, and what's contoured here is strontium isotope ratios and neodymium isotope ratios. And without really getting too much into the specifics here, these take a while to develop, these differences in these ratios. There's a clock associated with them. And so this level, the fact that we can make these contours and that there is this heterogeneity tells us that the mantle has some heterogeneity at very fine scales. In fact, at the finest scales that we look, it has heterogeneity expressed. So these are the sorts of observations that one has to get at. Here's another way of kind of looking at that same question. This paper looks at heterogeneity along the mid-Atlantic ridge, the northern mid-Atlantic ridge. Well, no, actually the whole mid-Atlantic ridge. And so each of these little box plots, these mini plots, is basically something that varies with latitude. Oh, it's really fuzzy. I apologize for that. So this is lead isotopes versus latitude, and here we have strontium isotopes versus latitude. We have a variety of components. And this allows you to see both the general homogeneity, that sort of spectrum of homogeneity along the mid-ocean ridge, but then you can also see the influence of various hotspots, and you also see that there is a little bit of variability in the scale of heterogeneity. So there is some spectrum of heterogeneity along the mid-ocean ridges. There was a project a couple of years ago to try and do something similar for the East Pacific Rise here at CIDER. And it got a certain distance along, and as a project, it would be something that someone could revisit. There's a lot less data. There's big gaps in the data for the East Pacific Rise because of its remoteness. So that limited the project to some extent.
Louise, is the bottom curve topography?
Yes, thank you. The bottom curve is bathymetry, basically. That light curve is exactly the same in all of these.
So if you didn't know where the hotspots were, you would never guess, actually.
Yeah, isn't that interesting?
unless you had the geochemical data.
Unless you have geochemical data. Mm-hmm. Yeah. So there's a lot of rich data in here. So then one can also ask, what happens at the scale at which we could walk up to an outcrop? And this is not universally accepted, but it's an important study, very important and influential study by Kellogg and Turcotte, in which they looked at an exposed peridotite, at the banding in this exposed peridotite, and they proposed that the banding was basically representative of mantle scale heterogeneity that had been in place in this peridotite, and therefore was accessible to measurement. And in doing that, they looked at oops, that's also cut off. They just computed the number of bands and their width. This scale is in centimeters, so 100 centimeters, and sort of the number of bands, and found this cascade, essentially, of that banding. And then a few years later, Alan Levander and his colleagues did a seismic experiment in which they also looked at scales of heterogeneity, and then they took this chart and put it on the same scale to see if they could, and proposed that there may be basically a spectrum of heterogeneity in the mantle, in the upper mantle, that really falls along this log plot, along a straight line along this log plot, implying a spectrum of heterogeneity of that sort. So that's something to keep in mind. Okay, so when Kellogg and Turcotte did that work, they proposed that the structure of the mantle is like a marble cake. And here's a picture of a marble cake, a marble cheesecake to be specific, to give you a sense of what they were talking about, where you can see that, just by incomplete mixing of the chocolate and vanilla batter, you get basically these different scales of heterogeneity. You get banding and so on. So the idea was that maybe that's what the mantle looks like. And then by extracting melt from that, you would get some sort of averaging in the upper mantle, which would give you the more or less well-mixed upper mantle. And then maybe the hotspots would be extracting from some other less homogeneous region. So that's the idea. Okay, so in addition, of course, we have seismic observations of structures in the lower mantle. So I have just basically borrowed all the content of this slide from a talk that Quentin Williams gave last week. I even preserved the yellow background. So this is mainly to remind you that the lower mantle has structure that plays into this, and that we don't fully understand what these structures are. So the LLSVPs give us a very large scale structure that are thought perhaps to be very long-lived, thought to have sharp boundaries in places, have quite a bit of complexity and structure to them, and may actually be an indicator of some long-lived heterogeneity in the lowermost mantle. So that's something we also have to take into account. And that is basically another observation that any successful model of mantle convection has to satisfy. And I like this quote that this thing that Quentin said, which is the bridge has not been fully built between the composition, structure, formation of LLSVPs, and we could say the same thing for mantle heterogeneity in general. So that's something. Okay, so trying to reconcile all of these different observations leads to drawing of cartoons. And so here are 4 cartoons of millions, maybe not millions, that was an exaggeration, dozens, that have been drawn over the decades to try and explain this mix of heterogeneity and homogeneity. And the thing that these have in common is that they typically have a sort of larger volume of material from which the mid-ocean ridge basalts are extracted that is mostly the same. And then they have other regions that are different and perhaps are the origin of ocean island basalts. There are some problems with some of these models. For example, this model isn't really compatible with current understanding of seismic observations. Moreover, one would expect that this lower layer here would be as well mixed as the upper layer. It might be different, and so it wouldn't give rise to the full scale of heterogeneity that we require maybe something like this or something like this. This is my preferred model, or something similar to it, would satisfy that need. This model has the heterogeneity kind of uniformly distributed throughout the mantle, and so that also is difficult to make compatible with the geochemical observations or the seismic observations. Okay, that was motivation. Let's talk now about mixing. And this is also from Otino. He had a paper in Scientific American quite a number of years ago, but it illustrates just the basic, it's a cartoon of the basic processes. So you start with a blob of dye in a material, and you impose some flow on it, and the mixing occurs by stretching and folding, something I've already mentioned. So stretching that blob to make it elongated and folding it is going to create a region that is a mix of these two, yellow and green. When the bands get thin enough, the sort of ultimate mixing occurs by molecular diffusion, if these are miscible fluids, miscible materials. So in that case, the sharp boundaries between these are going to be smoothed out by molecular diffusion processes. These happen at such small scales in the mantle that we are really not going to consider them much beyond this slide. But there are processes in the mantle that may smooth out heterogeneity. For example, melting and melt extraction can act in the same way to basically mix or do that last stage of mixing of these heterogeneities. Then we can also have things like breakup of the banding into droplets. And what Otino has in mind here is a situation where you have surface tension that will cause that to happen. But this also could be seen as a sort of boudinage kind of process. And that's going to tend to reduce the amount of stirring because these blobs are not going to be changed much. And so this is really emphasizing the role of viscosity contrast. This happens when you have a viscosity contrast between the two, between the green and the yellow. Okay, so let's talk about some terminology. These two terms are important to distinguish between, and yet we are going to use them casually interchangeably. So when we talk about mixing, we really mean a combination of that stretching and folding process plus the diffusion that completely homogenizes two different dyes, okay, the green and the yellow dye. When the correct term for the stretching and folding is stirring. That's really a mechanical process in which the material's surfaces are elongated and the length scale of the heterogeneity is reduced mechanically. And so when we talk about, because I said diffusion is not really, it really only occurs at the very finest scales in the mantle, we probably should really always refer to this as stirring, and yet we sort of casually convolve these two terms. So I'll continue to use both stirring and mixing through this talk. To understand the flow, we're going to use, we will often use tracer particles. We'll introduce tracer particles, and that can be a dye, or more likely in a numerical model, it's going to be an infinitesimal marker that moves with the flow. So if we have a velocity field, we can basically integrate that through space and time in order to follow the infinitesimal marker. And these markers can either be passive, in which case they just go with the flow. They basically just flow, and they are just used to see what's happening. Or they can be active, in which case an active tracer would basically influence the flow. So it might be more dense than the material that it's embedded in, or it might cause the viscosity to change. And so that tracer is going to basically affect the flow that it's in. So it'll modify the flow by its presence. So those are just terms to keep in mind. Another thing to keep in mind as we go forward is that the mixing scales that we are used to in everyday life are quite different from the mixing scale in the mantle. And there are two scales, two sort of numbers to keep in mind here. One is the length scale, which in geophysics and mantle convection is thousands of kilometers. And the other is a dimensionless number called the Reynolds number, which is basically a measure of the inertial forces normalized to the viscous forces. And all you need to know for this is that the higher the Reynolds number, the more turbulent the flow is. When the Reynolds number is low, the flow is known as laminar, and it doesn't have small eddies, which will help mix the flow. So this is a bunch of different things, food engineering. So when I use food analogies like the toffee pull and and the marble cake. I'm using that because basically it fits with this low Reynolds number flow, but it also is at a length scale that we human beings can understand and grasp readily. If we go up, I put Jupiter on here in honor of the Juno mission, which just basically went into orbit around Jupiter. So Jupiter's mixing scale would be somewhere up in here. Sort of astrophysics and oceanography and atmospheric dispersion are up here in the turbulent regime as well. And so that means that we can't really use analogies from oceanography and atmospheric science as well to understand mixing in the mantle. So bear that in mind. Yes?
Just to use the light, please, for what you reminded everybody that they need to use the mic. Curiosity.
Is it on?
Can you turn on the volume now?
Out of curiosity. Where is the solar nebula mixing on this scale? Does it scale up to the right or down to the right?
I think it's, oh gosh. Well, the length scale is really long, right?
Yeah, huge. So it's way off.
It's way off there,
but the
yeah.
question is the inertial forces to viscous high?
I think it's high.
High, okay. Thank you.
But I don't know. Someone that can correct me if I'm wrong about that. Yeah, okay. So I'm going to attempt to show a clip from the Fluid Dynamics film series. We'll see how this works. Okay, let me make sure I got the timing right. So this is kind of goofy, but in the 1950s and 60s, early 60s, the National Science Foundation and a group of mechanical and aerospace engineers got together and made a series of films about fluid dynamics. And these are done by some of the giants of 20th century fluid dynamics, and they're quite interesting. They have the pace and so on that you would expect from films of that time, but the experiments are beautiful. And they would be hard to, I think they were designed for teaching because it would be hard to reproduce these experiments in a typical undergraduate lab on a kind of everyday basis. So a few years ago, someone at MIT digitized them all and made them available for free. And so you can look at them and try them out yourself and see what you learn from them. So the one I want to show you starts at a few seconds from now, I think. Uh-oh. Let's see. Okay. So kinematic reversibility. So I'm going to talk you through this rather than showing it to you, rather than letting him talk, which is kind of unfair of me. So basically, what we're looking at here is a tank of sugar syrup. And that tank of sugar syrup, this is a low Reynolds number flow, and he's going to talk about mixing. Maybe I should, what do you think, Michael? Do you think I should just have... It's G.I. Taylor, yeah, I know. So, if I turn on the volume, will that...
The annulus between them is filled with glycerine. Into this space, I introduce some dye, which stays put owing to the high viscosity of the glycerine. Note its position before I start turning it. I now turn it 4 times, pushing the handle clockwise. The dye seems to mix as a drop of milk mixes when it is stirred into a cup of tea. Now I reverse the direction. And after turning exactly 4 turns, the dyed area reappears in its original position, with a little fuzziness due to molecular diffusion. To see what happens, we have a second apparatus that is filled with syrup. It has a wider gap, and we can look down on it. A little colored syrup is injected to mark the fluid. When the cylinder is turned, this fluid is stretched round the annulus. Now the inner cylinder is turned back exactly to its starting position. During the forward motion, the boundary of the fluid follows a path determined at each instant by the motion of the wall. At these very low Reynolds numbers, particles within the fluid move when the boundary moves, and they stop when it stops. During the reversed motion, the boundary of the fluid retraces exactly the path it followed during its forward motion, and the particles return to their original position. The motion of a rigid body is also reversible. Here is one with a gap to mark its orientation. This is set initially in the 12 o'clock position. The motion carries the body around and also makes it rotate. On reversing, the rigid body returns to its original position and orientation. If, however, a flexible body, like this bit of yarn, is inserted, the reversal of stress will alter the shape of the body so that it will not return to its original position.
Okay. Stop that. So the reason I showed you that is because it's such a nice demonstration of the processes that we're talking about. And also, I just love those. So the whole series is marvelous, by the way, and very accessible, very straightforward, really beautifully put together. And these are really, truly the giants of 20th century fluid dynamics talking. So it's interesting to look at them. I use them in teaching all the time, and I never get tired of them. So what the point of that clip, though, was that without diffusion, that mixing could be reversible if the flow is reversed. And there was that difference with the string when you put a piece of string in where it folded a little bit on its way back as well. So when we're trying to understand what's going on in a mixing scenario, we have to pay attention to the flow, and laminar flows are going to behave in this way where we can have both mixing and unmixing. And so that may help us preserve heterogeneity in a flow that we might otherwise expect to be well stirred. Okay? So one thing to note about this, and I'm not going to go through all the mathematics of it, but I just want to point this out, is that these are concepts borrowed from structural geology, right? So in a simple shear situation, which is essentially what he was showing you, where we have a box or a tank of fluid and we're shearing one end one way and the other end the other way, then our blob of dye here is going to be stretched and rotated. And that stretching and thinning, so it'll be thin, and we could measure, it'll be thinned, elongated in one direction and thinned in the other direction. We can measure the rate of thinning with time. And in a simple shear situation, that thinning is going to be proportional to the strain rate and time. But if we have pure shear, where we are stretching, pulling, and then thinning in the other direction, that rate of thinning is going to be exponential with the strain rate and time. And so in a flow, such as any kind of mantle flow where we have a mix of both pure shear and simple shear, where we could, in fact, break it down into those if we wanted to, the mixing, the stirring is always going to be dominated by the places where we have pure shear. And so most of the mixing is going to take place, for example, at places where you have pulling apart or coming together, such as such as mid-ocean ridges and subduction zones. So that's something to bear in mind. So I'm not going to dwell on this, but Peter Olson, Dave Ewan, and Derek Balsiger, way back in 1984, thought about this and thought they published 2 papers related to this. This is one of them, in which they said, well, what happens if we introduce heterogeneity at a certain scale, such as, for example, subducted slab, which is going to be, I don't know, 80 or 100 kilometers, or maybe oceanic crust, it's going to be 6 or so kilometers, right? What happens if we continuously introduce that into the mantle, and then we think about how the scale is going to change? And so they kind of worked out, basically, without a lot of fancy numerics, they worked out this cascade of decay in which basically the thinning is going to increase with time, and at some point we'll reach the point at which we can no longer resolve the heterogeneity. And at that point, the scale of heterogeneity will drop off due to diffusion. And so you can think of the mantle as having this cascade of heterogeneity in which larger scale heterogeneities are thinned and thinned and thinned until eventually they are dissipated, meaning that they are below the resolution that we could see them by any means that we have currently available. And you'll note that they cleverly did not put a particular specific scale on this, which means that that scale of resolution could move with time as our detection limit improves. But the idea is that basically you introduce heterogeneity at a certain scale and it will decay with time because of that folding and stretching. So the real question is, what scale can we see first? And then what scale does the heterogeneity look like, whether we can see it or not? Right? That's our mixing question. OK, so what about chemical diffusion? This is just a way of reminding you that chemical diffusion is not really going to make a difference in the mantles. This is, again, a simple situation where I have a linear, basically a band of heterogeneity in a thinning flow in a pure shear rate, and basically looking at how sharp does that boundary remain over time. And this started out as a 6-kilometer thick ocean crust, and it is not until it gets down to a few centimeters across in the mantle that molecular diffusion takes over and creates the mixing. So that mixing in the mantle is likely the final sort of stage of mixing by diffusion, really only occurs at a very, very fine scale, probably much below the limit of any detection means that we have currently. So that mixing stage by diffusion is probably not relevant in the sense that we can't observe it. OK. So let's bring this to the mantle. OK, so this is a very simple model. It's not intended to be the mantle. I'm going to pause it for a sec while I describe what just happened there. Whoops. OK. So it's a very simple model. This is a flat layer Earth. So a flat Earth, it's heated from within. So there's no hot thermal boundary layer at the bottom of this. But it's cooled from above. So there's a cold thermal boundary layer. And that cold thermal boundary layer is really controlling the flow. Okay, so there's no viscosity variations. This is the most vanilla convection you can possibly imagine, except for the fact that it's internally heated. And I've introduced here 300,000 particles, tracer particles, in that tiny little dot with very, slightly different positions from each other. And then we're going to watch what happens to them. So as the flow progresses, we have these downwellings. There's really nothing making them subduction because there's no viscosity contrast, so they're just merging in some way. And you'll notice that that blob has stretched and it's folded. So you get this nice kind of folded thing. When it hits that point of downwelling, it tends to stretch. And it stretches and folds, and then it kind of, as it comes back around, it tends to basically come back together. I think it looks like a seahorse here. Anyway, it tends to come back together into a single blob. So that's sort of similar to what we saw in that laminar flow video. But at some point, it gets split by a downwelling. And at that point, we really can't go back. So what's happening here is that at these points, there is exponential thinning and there's basically pure shear, and so there's exponential thinning and stretching, and that is where the dispersion of the particles is happening. They could go around the center of this for quite a while without really changing, but anytime they get near one of these stagnation points where there is basically exponential stretching, they are stretched, and that's where most of the mixing action is happening. So So heterogeneity can be preserved in the interior of a convection cell as long as it doesn't get to a place where there's this kind of stretching. But once it does, then there is basically lots of stretching, and that's where most of the mixing happens. So you asked about the dye, right? This is basically just many particles. So they started out as one. It doesn't look like the area of particles is conserved, but it actually is. It's a visual effect of having them more dispersed. That in this case, they're finite, they're infinitesimal points, but they're drawn as finite size points, and so they look like they fill up the whole thing. So there's some interesting things going on here. For one thing, we get that kind of banding. We get that stretching and thinning. We also have pockets that are really not fully mixed with the other pockets. And then we have a sort of global scale of lots of particles over here and somewhat fewer over here. And all of these things can occur in models of mixing. So this leads us to a question of how we're going to then analyze that kind of result. That's a very nice illustration, but how are we going to analyze it? And so here are some popular ways to do this. And you can kind of pick your favorite depending on what problem you're looking at. So what we just saw is basically introducing tracers. Those were passive tracers into a model, and then monitoring the dispersion of them. And we just looked at them visually, but we can also use various statistical methods. A box counting method in which we basically divide up the computational regime into boxes and then see how many land in each box, or you can use your other favorite statistical method. So I'm not a statistician. I'm going to show you one method that people use, but you may have better ones, and I would be interested in hearing about them if you do. The other thing we can do is look at the fine scale mixing, so treating each marker, each tracer, as a strain marker, and then computing how deformed it gets. And the typical way that's done is either by what I just said, treating it as a strain marker in the sense that structural geology uses. Another way that's done is to basically take two tracers that are very close together and treat their increasing distance as a measure of stretching. And this is this is called the Lyapunov exponent if it's exponential. We basically can compute the exponent that goes with that exponential stretching and thinning. So that's borrowed from complexity theory, from nonlinear dynamics, right? That's a little bit problematic when we're dealing with a mantle convection model because our particles can't get any further away than the box they're in. Right? So typically the way we do this in practice is you take two particles that are very close to each other, you compute the stretching after one or some small number of time steps, and then you put them back together again. And so then you're basically renormalizing their position at every time. The other thing we can do if we're interested in basically confirming or if we're interested in using isotopic signatures to falsify our hypotheses, which we should be doing, we can compute the derived properties like the predicted isotopic signatures of a model. That has some pitfalls because the clock associated with basically the isotope systems of interest is a clock, and it introduces a time scale into the problem that may not be the same as the time scale of our mantle convection calculation. So we have to be cautious about using that, but it is a useful way to do it. Okay, I'm just going to kind of quickly go through a use of a statistical method to just illustrate what I mean. And so this model, this is a series of models. The details don't matter too much, but we were interested when we did this in whether we could maintain heterogeneity in the mantle by really bumping up the viscosity of the lower mantle. And so we started out with that generic vanilla convection, actually slightly modified because this is also temperature dependent, so it's going to have a nice immobile lid on the top of it. And then we said, let's increase the viscosity. We also increased the thermal conductivity of the lower mantle to really try and shut down convection. I want to create a model in which there's no mixing going on in the lower mantle, so I can create that source of ocean island basalts. Let's see if I can do it. And so we increase that. This factor F is basically the factor by which we increase that viscosity. One thing you'll notice about this is that when we do that, it makes the convection in the lower mantle very sluggish. So I don't know if anybody talked about streamlines, but these are streamlines, and they're contours of a stream function, and they give you a sense of how fast the flow is moving. The lines that are closer together are imply a greater velocity than the lines that are further apart. And so we've got sort of sluggish convection going on, and as a result, the model heats up because it can't get the heat out as well. So that red, that intense red, this is temperature. The color is temperature here. That intense red means that we're not removing heat very well. These models are not realistic. I think these models would start to exceed the melt temperature of the lower mantle. So they're clearly not right, but we were exploring one parameter, the viscosity. So our reference model, this is back to using tracer particles again. And in this case, we just put them everywhere so we could do some statistics on them, and we color-coded them by the 4 quadrants. And so the idea here is that you can see the 4 quadrants when we started, and then they quickly start to disperse. We get that banding, and over time, they are very, very well homogenized. So let's see what happens when I bump up the viscosity in the lower mantle. When I do that, the flow changes. First of all, it's dominated by this 2-cell flow. And second of all, in that transition zone, where the viscosity increases, I have these pockets that are really isolated from the rest of the mantle. So what is going on there? Well, this is something that occasionally appears. These are essentially regions the flow is moving entirely around those because it's organized around this central, around these large-scale flows, but it never really gets in there. So these pockets of heterogeneity are preserved throughout the entire run. However, yes?
Sorry. For this simulation and the one before, would you consider this low, if you were to calculate the Reynolds number, is this low Reynolds flow?
Yes. It's all
so
low
you're
Reynolds
using,
flow.
even in the upper mantle, a high viscosity?
All of it is high viscosity. Yes, all of it is very low Reynolds number, essentially 0. Yeah.
Are the interior regions that are not well mixed, are they gradually getting eroded?
Repeat the question.
Yes. So.
Yeah, I was just asking about the interior regions here, if they're gradually getting, say, eroded or mixed, basically.
They do appear to be, and what I have not done is gone back and seen, like, I think the quadrant, it looks like this is getting entrained in there. But that also, I think that region of unmixed stuff, actually, the boundary between the quadrants that I marked in this way probably is slightly within that area. So I don't know whether they're truly being eroded away or not. There is clearly some exchange of material, but that material might have been in there in the first place. Yes?
So are there other ways to have tracers track the flow? Because it looks like these tracers are essentially following the flow. So
yes.
I'm sure there are technical terms for that. Like, just static tracers, just look at one pixel in the domain and see how that is changing.
Yes, we could do that. We have not done that. We've tended to use the tracers as basically in this way to try and trace the flow in some fashion and then look at what happens to them from there. Right. So this work could be advanced, actually, because we have a lot more computational power than we did. Now I just want to show you one last one of this where we've bumped up the viscosity in the lower layer even more. And we've lost those isolated zones. So those isolated zones are somehow a little quirk of the previous model. We caught by luck. I have not had a mathematician who specializes in that sort of thing look at this to help isolate what's going on there, but because I was really doing these with an interest in mantle convection. The thing I want you to see here is that the lower mantle in this case really does have very, very sluggish convection. Oh, I shouldn't have put that down there, should I? No, okay. Question.
Thank you. Sorry to interrupt, but
That's okay.
Can you give us a sense of time scale? I know it depends, but like when we watch one of these movies before it repeats, is that like 4 billion years?
It's not quite 4. It's probably like 1 billion.
Okay.
Yeah, probably like 1 billion. In that range.
Thank you.
Yes.
It seems like
Wait. Oh.
Wow.
competing.
Okay.
There you
We can
go.
have a duel.
Yeah.
It seems like in the slightly less F simulation, where you preserve those cores, I didn't catch it, but it seems like here the downgoing stuff goes down to your highly viscous layer,
Yeah.
and then gets laterally transformed,
That's right.
and it kind of mixes up. Whereas before they were plunging to the bottom.
In both cases, they are actually plunging to the bottom. Oops, that's. In both cases, they actually do make it to the bottom, all the way to the bottom. Right. So everything makes maybe a little less, yeah. I mean, the thing that has struck us in looking at these is that the flow in the lower layer here, this extremely viscous layer, is in fact very sluggish, but it doesn't prevent mixing because most of the mixing happens in the upper layer. And then these packets of pretty well stirred stuff get kind of moved into the lower layer where they get stretched and deformed slowly, and then they come back up again. So this increasing the viscosity of the lower layer did not accomplish what we thought it might. It did not basically it didn't isolate the upper layer and the lower layer.
Louise,
Yes.
this is for a purely heated from within case.
Yes.
What would happen if you added a significant component from
Of heating from below. So what would happen if we heated it from below is we would get plumes coming off. We would get a hot thermal boundary layer which would become unstable and would basically produce upwellings. And those would contribute to the mixing as well. They would add to the mixing. The reason we didn't do that in this is because in 2 dimensions, that is an infinitely long sheet of upwelling. It cuts across the whole layer. Just as the subduction zone, the downwellings cut across the whole layer. And so we thought that would enhance the mixing too much. Whereas in the Earth, those upwellings appear to be more pipe-like and therefore do not cut across the layer in the same way. Yes?
And what will be the effect of periodic boundary conditions?
Of which? Periodic boundary.
Periodic boundary conditions.
Yeah, so this actually does have periodic boundary conditions. It's a little hard to see, but it actually does. So we've done things with different boundary conditions, actually. You could also ask what would happen if we did this in an annulus so that things were moved around. You know, there are various kind of perturbations one can make on this. Mm-hmm. I think there was one hand, oh, yes, okay. Several hands up. I may not get past these movies. We'll see.
So another question, maybe you can comment on this. On average, right, there's good mixing.
Yeah.
But it looks like statistically the domains are still partitioned. So
yes.
Essentially, maybe the chemistry is governed by those. I don't know.
That's right.
Tracking the flow, essentially.
Yes, you are observing that correctly. That globally there is, more of the blue and green on this side and more of the red and yellow on this side, and that doesn't change over time. So globally, there's some scale of heterogeneity that is produced by this process that is not lost. And so, maybe that, and there are global heterogeneity scales in the mantle, so that could be one of them. I'm going to move quickly on if there's not another question about the images. We can always come back to these videos. Okay. So it was 4 billion years that we ran the whole thing. There it is right there. Just to recap, basically, the particles that started in the lower left quadrant here have dispersed in this way. And so you are seeing this kind of global variation in the distribution of the particles. But in that starting point, they're very well mixed. So how do we quantify this? Well, one method to quantify this is known as configurational entropy. And you're going to see here both the strengths and limitations of this method. So this is a statistical method. It's not entropy in the thermodynamic sense. It's entropy in the sense that it's looking at the disorder of a suite of particles that start out ordered and basically computing how disordered they get with time. So you can do this by starting with a blob and seeing how it disperses, or you can start with particles everywhere but have them uniformly spaced on a grid and then see how off from that grid they get. And you can get a measure of entropy that will increase, configurational entropy, which will increase with time. And what you'll see here is that in that sort of generic vanilla convection, that entropy increases an entropy of 1 means that it's well mixed. So that entropy increases very rapidly and then levels off at 1. And as we increase the viscosity of the lower layer, that entropy takes a little longer, quite a bit longer, to rise to 1. But it appears to rise to 1. So when we are looking at this kind of global statistical measure, configurational entropy, it looks like it's pretty well mixed. There's some scatter, but it looks like it's pretty well mixed. And so that does capture the mixing a little bit, but it doesn't capture that global variability, and it doesn't capture those isolated regions. So this sort of statistical measure is good on the one hand. It helps us understand the evolution of the model with different material properties, but it doesn't capture the fine detail, and so that's its limit. That's the limitation of that. So we're still kind of working on that. Okay. I want to say a few things about 3 dimensions, because everything I've shown you is in 2 dimensions. And so 3 dimensions have a lot of complexity. In 2 dimensions, for starters, one thing I didn't say earlier is that in a 2-dimensional steady flow, meaning the time derivative is 0, meaning the flow doesn't change with time at all, you won't get mixing. Basically, the particle paths will follow a closed curve, and they will be reversible in the same way that G.I. Taylor showed you. You're not going to get mixing. It's only when you have time-varying flow that you get mixing in 2 dimensions. But in 3 dimensions, that isn't true. A particle path can be very complex, completely chaotic in 2 dimensions without the element of time varying. And so that really complicates our job of computing mixing. So this is a model by Peter Van Kecken and Suji Zhang in which they introduced just 1 tracer into this model, or 3 tracers, blue one, a red one, and a yellow one, and they're following their particle paths in 2 different steady state flows with time. And you can see how complex those paths are. Along the same lines, there are 2 papers to pay attention to. They did this in 1999, and then there was a review paper in 2002. This is introducing a block of tracers into a flow, and it's modern plate flow. In other words, they've imposed the current plate, a model of the current plate velocities on this, and let it run for 4 billion years. And so you'll notice that the particles are now dispersed pretty widely, again with some evidence for concentration of them in some regions, and they haven't made it everywhere in this model, but they certainly have dispersed. The other thing that you'll notice probably about this is you really can't see what's going on because it's 3D. It's very hard to know whether this is a bunch of particles all like in a narrow band or whether they're scattered throughout a large volume. Very, very difficult to know.
What's the viscosity structure here? Do you know?
Well, this is, I believe, a kinematic flow, so it's really driven entirely by the plate boundaries. So it's purely, uniform viscosity, I think, with that plate boundary driving it. So it's all driven by plate motion. Okay, so this is a really simple, again, box model, with a bunch of particles in a box, and it's just to really drive home the point that once you get into 3D, you get this kind of flock of birds effect here, but I can't really tell whether that fine banding that we were observing in 2D is coming into play here. Maybe there's some evidence for it, but because it's 3-dimensional, it's extremely hard to visualize and hard to study. So you now have seen some of the, you've seen one statistical measure which didn't completely capture what's going on, and you've seen now some, like just looking at what the flow looks like, and that's got some limitations too. So this is still actually an open research challenge, how to interpret 3D mixing of tracers. So, another way to do this is to go back and say, this is another method that I mentioned, which is to treat each of those tracers as an infinitesimal strain ellipse, and then compute the strain that happens. And so I'm just going to give you an illustration of what that might look like. Now, we did not invent this method. I'm showing you this model because it's simpler than the paper that invented it, so it's easier to describe what's happening by way of introduction, and then I'll show you the original work. So this is a model that is not thermal convection at all. It's just a box, and it's got some viscous fluid in it, and it's being driven by a plate that's going that way and a plate that's going that way. And it doesn't really matter what the velocities are or anything. We have a straight fault here, and then we introduce a couple of transform faults, and we vary the length of the transform faults. And so I wanted to show this. So this model is essentially two-dimensional, right? There's nothing going on in the third dimension. It's just a box with this plate pulling one direction and the other. And so in that essentially two-dimensional model, if I introduce a red particle and a blue particle, they have a closed path. And that closed path just goes around the loop. It goes around there forever. So, but I can still compute the stretching everywhere for particles everywhere in here. And this is a model, basically just a visualization of the stretching that goes on here. And as you might expect, the stretching is maximum when the particles get near to that extensional zone where the stretching is exponential. And there's a lot less stretching in the center where they're far from that. So that's not a surprise. The way we visualize this, what's going on with these particles, is by something called a Poincare map. So imagine I take a slice through the middle, a horizontal slice across the halfway point here, and I create a plane. And every time that particle path crosses that plane, I put a dot there. So this blue path now collapses to two dots, one there and one there, there and there. And then the red path collapses to two dots. So that's pretty boring because I now just have four dots. But if I add a transform fault to that model, things become extremely complex. Okay? So now I've added some transform faults to this. I still have only two tracers, a blue one and a red one. And their particle paths now look like this. The blue one looks very complex. The red one looks a little simpler. And the Poincare map reveals some really interesting behavior. The blue, every time that blue particle crosses the middle, you get a dot. And every time the red particle crosses the middle, you get a dot. And you can see that we are sort of getting these isolated regions, which is where the red particle is confined to, and these much more dispersed regions where the blue particle is confined to. So our stretching map is also much more complicated. This is basically the Lyapunov exponent, that exponential strain rate factor. And it's a little more messy here. Maybe that will be useful. Maybe this will be useful. So the people who really thought about this first were Sylvain Farachat and Yannick Ricard. And they computed something similar, looking at these chaotic trajectories before that illustrative model that I just showed you. So this is basically their Poincare map of a simple flow with one transform fault on it. That's just remarkably simple. The flow is remarkably simple and yet leads to this massive complexity. It's a little bit daunting when we think about how to interpret that for the Earth. They computed 50 Poincare sections, meaning there are 50 particles. Each one of the colors is a separate particle. So we have red and orange and blue, green, purple, etc. And you can see how complex they are, these paths. They also computed this Lyapunov exponent and mapped it out. So this is a measure of how much stretching and folding there's likely to be. And so the hotter the colors, the closer to red they are, the higher that Lyapunov exponent. And the blue, the closer to blue and that lavender purple color is basically the regions of very low stretching. So we're seeing various cross sections. And what you're seeing is that there are regions in which the stretching is really extreme, and you expect a lot of mixing in those regions. And then there are pockets in which there's very little stretching, and they are isolated from one another. That's revealed by the Poincare maps and also by these Lyapunov exponents.
Those are vertical cross sections?
Yeah, they're horizontal cross sections through the middle, I think. Yes. No, at different times. There are 4 different models, actually, with 4 different transform fault configurations.
Time doesn't matter.
Time doesn't matter, that's right. These are instantaneous flows. They're just they don't change at all with time. So there are 4 different models. These may be vertical and these horizontal, actually, of the same model. Right, because here's the transform fault. Here's the transform fault arrangement, and here's the transform fault arrangement for this one. So there's a very slight difference with them. So these are the vertical and these are the horizontal. So they're showing you basically how complex mixing is in 3D in this steady state flow, or how complex stretching is, I should say, or stirring in this steady state flow. So we're still looking for ways to, to address this. The last kind of method I want to at least bring your attention to is computing predicted isotope signatures. And so this is by Xi and Tackley, and about 12 years ago, and there's still work of this sort going on. It's still a productive way to approach it. So there's a lot on this figure, so I'm just going to highlight a couple of things. So they have a model of convection. We're back to 2D again. We're back to basically an annulus. So we have a model of convection in which they have a core and a mantle, and there's convection going on 1 billion years, 2 billion years, 3 billion years. I think this is forward time. And you're just seeing the convection. And then they've introduced tracer particles, but those tracer particles have properties attached to them. So this field is, so the way to read this is that that's 1 billion years, that's 2 billion years, that's 3 billion years. The columns are basically the time snapshots. And then each of these rows is a thing, a quantity that's being shown. So the temperature is the top quantity. The next one is the concentration of particles. The third one is the age of the particles, and so on. And they have some rules for introducing these and removing them, which is why you get an age. But then the last three are basically an isotopic signature associated with each of those tracer particles. So the tracer particles have a clock. They're decaying, and they are producing the appropriate lead isotopes or samarium isotopes, and these are being tracked. And so basically each of the colors here is giving you what the isotopic composition is of a packet of fluid based on that convection model, the introduction and elimination of the tracer particles, and how it has aged. So the big challenge here, or so there are many challenges here, but one of the big challenges here is that because we don't have a full picture of mantle convection as it decays with time, but we've introduced a clock, we've basically introduced some time scales that may or may not be appropriate for the time scales of our convection calculation. So that makes it a little bit challenging. It's something to pay attention to. But nevertheless, this is what happens. So now what they end up producing for all of those tracer particles, each one of these small graphs is basically an isotopic correlation diagram. So this is a lead-lead diagram. I think there's a neodymium. Is that samarium or strontium? I think that's a samarium diagram. So they basically are producing correlation diagrams between the different isotope systems that they're tracking, and then looking at what they should be. And so then they correlate that with, or they basically use that to rule out models that don't have the slope that you would see predicted from observed mantle isotope geochemistry. And so that's how they can throw out models and they can leave models in. So they're using those isotopic correlations as a predictor, as a test for falsifying hypotheses or leaving hypotheses in. So that's basically a method that has been used in a limited way, but used nevertheless. Okay, so something I've not really gone into is the role of viscosity contrast. So we increased, in that one model that I showed you with those nice movies, we increased the viscosity in the lower mantle. But it may be that the mantle's viscosity is variable due to composition. And so Michael has basically done quite a while ago, a series of computations or calculations of the effect of that, starting with a spherical blob and varying the viscosity contrast in a simple model of flow in order to see what happens to it. And you can see that you do get sort of stretching and tendrils that develop while maintaining some of these blobs, depending on the viscosity contrast between the two materials. So that's a complexity that we have to consider, and I won't say anything more about that. Let me wrap up. Okay, I think I'm close to the end of time. I haven't kept track. So we talked a little bit about the motivation for understanding mixing and stretching. We mentioned that stirring, which is really the operative process, is controlled by stretching and folding, and that stretching and knowing where that stretching and folding is and how much of it there is in the mantle is going to really determine how much mixing there is. That stretching and folding creates a cascade of heterogeneities of multiple scales, giving a kind of marble cake sort of structure to the mantle, which was something we can probably observe. That mixing is complicated. We've really focused on laminar flow. Turbulent flow would be more efficient at mixing. 2D versus 3D is a really big factor in what is going on. And in order to understand the mixing, we have to pay attention to the scale of interest and the time scale of interest. And I really do want to make sure you keep in mind when studying this that the geodynamics, this sort of geodynamics cannot be done in isolation because mantle processes create and destroy heterogeneity. And without an understanding of those processes and those time scales, we have really nothing to hang on to when we're trying to understand mixing in the mantle. So let me just stop there and take any more questions. If there are. Yeah. Oops, where's the other microphone? Okay.
I was just wondering, so we talked a lot about laminar flow, and you mentioned right at the end you have a bullet point here about turbulent flow. Mm-hmm. How would turbulent flow be applied to mantle? Because usually when I think of turbulence, I think of inertial forces being important.
So mostly I want to emphasize that it doesn't really apply to the mantle. It certainly applies to the core. You can kind of think about those time-varying, very active mantle flows as being kind of thermally turbulent. It's really not turbulent in the sense that an atmospheric scientist would use turbulence. Still very low Reynolds number, but has things that look and in some ways act like eddies. And so that is a factor in the mixing, but it's not turbulent.
In all the models that we looked at, recognizing you'd have to impose a more complicated viscosity structure, can you comment on the role of one-sided subduction in preserving or destroying heterogeneity in the mantle?
One-sided subduction, right. So that certainly plays a big role in creating heterogeneity because of the action in the mantle wedge, the melting, the extraction of melt. So that's one of its biggest roles. And then you could investigate mixing within the mantle wedge. If we knew exactly what the flow looked like, that would be really helpful. And as you've heard from the talk about subduction, it's sort of complicated. So on a global scale, it probably plays a little bit of a role in isolating one side from the other. But on the local scale, it plays a big role in creating heterogeneity.
Hey, Louise. I was wondering if you could say a few words about how people actually go about sampling in these models.
Sampling? Yeah. In the models or in the Earth?
In the models, and how it relates to sampling in the Earth.
Yeah. So sampling in the models is strictly a matter of choosing bins to put things in, or choosing a sampling rate to put things in, and then computing the statistics. So you want to do something that has typically, when we're doing things like these configurational entropy, we basically vary the box size of our sampling until so we know that we're not being influenced by the resolution. But the resolution of sampling is something to pay attention to. In the Earth, the sampling is provided to us by the Earth for geochemical. Certainly for geochemical tracers, the mid-ocean ridges are where they are, and we can get to the ones we can get to. And there's now decades worth of data collection that we can mine, essentially. But that's often limited by the sort of practical considerations as much as anything.
So I was just wondering, like, in terms of if we think things we're sampling on Earth are mixtures of multiple components, how we can actually accurately sample that in the models in terms of the size of the region that you're melting, or how things are essentially being mixed into multi-component mixtures.
Right. So the models that really attempt to look at what the surface flow does to the interior, like the model by Van Kecken that I showed you, for those they can sample where the mid-ocean ridges are. So they can really map their sampling to the real world in a sense, right? For the models that I showed you that are more kind of general, you'd want to have some kind of sampling that matches in a statistical sense, I guess, the underlying sampling of the mantle in some fashion. I mean, there's been some studies. There was a study quite a long time ago by Pat Kenyon and Don Turcotte that looked at what the minimal scale is and said that when you have magma involved, the minimal scale in which you can sample is probably close to 1 kilometer in some sense if you're on a mid-ocean ridge. I don't know if that's been updated or not, but that may be the bottom line because mixing occurs at that spatial scale due to magmatic processes.
You showed a slide about where you compared the mid-ocean ridges versus ocean island basalt distributions of chemical heterogeneity. Are the models by Shi and Tackley and others, are they now successful in explaining those differences or not yet?
Many of the models focus on the mid-ocean ridges, and they basically focus on the whole spectrum of heterogeneity rather than on trying to get the specifics of a specific geologic region. And yes, they have been successful at doing that. I don't know how many models they have to reject, basically, to do that, because that's a big part of it.
And so when are they successful? Do you know which models, what are the characteristics of the models that make them successful?
That's a good question. I don't have a good feel for, I don't have a good feel for what are the most important physical characteristics, which I think is what you're getting at. What are the most important characteristics of those models? I don't really have a good answer to you.
Okay. I think I have 2 questions. The first one is about...
there you are. Sorry, I'm looking around.
The first one is about the breaking of the oceanic crust. So do you think the breaking of the oceanic crust plays important role in the mixing? For example, we know there are some faults in the oceanic crust created free surface. And so does it only increase the mixing of the oceanic crust, or then it doesn't change the conclusion about the very, very, very good mixing?
I'm not quite sure I understand the question, actually. Are you asking whether the crust itself, after it's subducted, is better mixed?
Yeah, after it's subducted.
Oh, I think once it gets under pressure, and it's going to behave in the same viscous way. Is that what you are getting at?
Yeah, because for example, in the subduction, we observe the breaking of the...
Right. So that would behave in some sense as those isolated blobs and then be mixed. But what's really going to control that is the viscosity contrast between that and the surrounding mantle. So as it warms up, it's going to basically start to stretch the same way.
Okay. Yeah, another question is... probably I missed some point here. So in your model, the viscosity, is it temperature dependent or just depth dependent?
Well, you didn't miss that. In the first models I showed you, it is not temperature dependent. And then in the models that had those movies, it is temperature dependent. So in these models, it is temperature dependent. So that means you have and I did not try and do anything to break the surface. So you have it's not totally stagnant. It's a weak temperature-dependent viscosity, basically. But the upper thermal boundary layer is slightly more viscous than the underlying mantle, and therefore tends to stagnate a little bit. It's not as big a contrast. It's something like a factor of 5 or so more viscous.
Okay.
Yes.
In terms... sorry.
But someone else has the... Yeah.
In terms of natural observation, going back to the paper by Alleger and Turcotte that you had, if you look at prototype massifs, I'm not aware of peroxenites if they are remnants of former oceanic crusts that are much larger than what they observed. So
Right.
it doesn't seem like it goes beyond a few centimeters or maybe 10 centimeters or so, but certainly not hundreds of meters or something like that.
Right. So that is certainly a, that's something to pay attention to. I mean, yes.
Louise, you were very delicate when you presented that paper, right? You said it's very influential conceptually and pedagogically. But since then, there have been lots of papers explaining how those approximate veins are made.
That's right. Yeah, there are lots of papers that explain how those peroxide veins are made. That's a very good way of putting it. But nevertheless, that concept has persisted. And so I think it's worth sort of showing where it came from and explaining why it's there and why it's called that, even if the original origin is, is different.
So one of the take-homes that I seem to be getting from this is that the length scale of heterogeneity in the mantle tends to decrease as a function of this mixing, but it's not immediately clear that that's what happens in the mantle, especially the lower mantle, if you have things like accumulation of slabs and piles and things like that. So can you comment on maybe there's an increase in that scale in some conditions?
Thank you for asking that question, because it gets to something I didn't talk about. So when we were doing this sort of work, we were trying to see whether we could invoke anything other than compositional difference to create that larger scale heterogeneity. And we have not found any way to do that, no matter how hard we've tried. And so that implies, to my mind, that the best explanation is some sort of compositional layering. That could be subducted, a graveyard for subducted slabs. However, you don't get all of the, the very, very, very long-lived heterogeneity that way. So it seems more likely to me that there is, a layer, that layer, the LLSVP or the super plumes, blobs, et cetera, are something that's been there a long, long time, and therefore must be isolated by an increase in density. Frank?
That was kind of my question.
Oh.
The role of dynamic of the delta rho rather than, say, using viscosity.
It's almost the only explanation left, basically.
So you preserve over 4 billion years.
Yes. Mm-hmm.
What's like 4% difference, intrinsic difference in density?
So yes, So basically, that sort of layer is best preserved when you have a ratio of the thermal influence on buoyancy to the chemical influence on buoyancy that's about 1, or slightly less than 1, right? So where the chemical buoyancy is slightly more important. If you have too great a density contrast, then you end up with a flat layer, which should be really obvious seismically, and also is going to heat up with time, and so then the heat transfer doesn't work, right? But if you have too low a density contrast, then you mix the two layers. So that's kind of the general range. However, that's challenging, right? Because the Earth's heat balance has changed over time. And so exactly, what that balance needs to be 3 billion years ago, when there's twice as much heat production versus now, is, and how do you preserve that over that length of time is still an open research question. Oh, yep.
So I'd like to...
Oh. Okay. I'm sorry, I'm not moderating very well. Go ahead.
Okay. Yes, okay. I'm here.
Yes.
I actually want to ask a perhaps naive question. In honor, because last week we heard a lot of geochemists talking about the major elements and the trace elements, right? So with the OIBs and MORB and everything like that, so that's what they analyze. I really like this mixing model, but if I understand correctly, this is still treated like a viscous fluid.
Yes.
But presumably the mantle is still viscous solid. And then all that chemistry, the elements will go along, as far as I understood, the fast path is always grain boundaries, dislocation sites, and so on and so forth. So wouldn't somewhere they will diverge from the viscosity mixing rather than they kind of go through those paths and become different?
So I lump some of that's a very good question, actually. I lump some of that behavior into a category that we would treat in this sort of model as diffusion, right? So all of that is basically going to be the homogenization that goes on at the diffusion level. But in terms of the viscous fluid, as under these elevated pressure and temperature conditions, that that solid material creeps, and so on a global scale and on these very long time scales, we can treat it as a very viscous fluid. And so that it's basically treated as a viscous fluid, even though it's solid. It's creeping flow that on the macro scale, really macro scale, is flowing as a viscous fluid would flow, which is why we can use the equations of motion for a viscous fluid to treat it. But then when we get down to the kind of compositional variations at this very fine scale, yes, those other, it's all a matter of scale in space and time. Those processes that you were talking about become more dominant. But from the point of view of the sampling length, they're still below the sampling length that we are likely to be able to see. So we sort of lump them all into diffusion, essentially. Laurent may have a follow-up answer to that. No, but okay, so.
Yeah, my question is very similar to what Wenlu just asked, because I'm also concerned about chemical effect. Mm-hmm. And the reason that I'm concerned about it is that there's a process that, from your talk, it wasn't really clear where I put that process into between two categories of creation and destruction, which is alteration or chemical reaction between the rocks. Yes, from the earlier experiment, that the diffusion scale is time scale is so slow that you can probably ignore the chemical diffusion and reaction for the history of the Earth. But it is also true that in all the Earth, temperature was a lot higher, and the way that the water stored and released would have been very different from what it is now. Then through the 660, you might have been having a lot of extensive hydrous melting, for example, if those observation of a little bit of melt of, pocket of melt observed in seismology is really possible at 660. So my question is that if you take into account the fact that Earth was very different in the beginning.
Yeah.
Not like these models where the system has been stayed constant throughout. Higher temperature, different mineralogy, different water storage, different melting at different depth. Would it really significant enough that we need to worry about, interpreting, isotope geochemistry, heterogeneity using the simple viscosity-driven models, ignoring most of the chemical effect?
Are you suggesting that the entire regime of dynamics was completely different during that time?
I wouldn't necessarily mean that it was completely different.
Mm-hmm.
But would that difference in early Earth would influence the pattern of isotope heterogeneity? A similar level or something that we have to worry about rather than just focusing on this viscous.
Right. Well, we don't know the initial conditions, so that's really problematic for doing these sorts of mixing models.
Are there any attempts or models that try to incorporate this type of things at all, or?
I think people are starting to think about that. I think I was trying to focus on the basic physical processes at play, but I think people are starting to think about that. But it's vexing because as you've seen, these models, the sort of the mixing consequences are quite sensitive to things that that we know about now, small variations that we know about now, and so the lack of knowing what the initial conditions are is really, really problematic for trying to do that. There are people starting to think about this, and I think Torsten's about to say something about that, maybe? Or no, maybe not. Okay.
Mm-hmm. Then question on
Yeah.
I just wanted to make a few comments about more, because I really didn't talk much about it in the mid-ocean ridge basalts in my talk, but they really do seem to be a well-mixed reservoir compared to everything else. Mm-hmm. It's certainly not completely homogeneous, but when you compare them with oceanic basalts on the one hand, and even more heterogeneous would be the continental crusts and continental lithosphere. Certainly look like a well-mixed reservoir. But I would also point out there are subtle differences in morb regions. So there's a North Atlantic and there's a South Atlantic and an Indian and Pacific regions which are subtly distinct in their isotopic composition, which is sort of consistent with your animation there.
Yeah. Yeah, I've tried not to overinterpret that animation, but there are many of these models end up having this sort of subtle global variation in the composition that results, and I think that is one possible origin of those global scale compositional variations that you mentioned. It really is remarkable how homogeneous the mid-ocean ridge results are, though. It's quite something.
So I'd like to ask you more about that sampling that has been discussed several times already, because it seems that whatever comes close to a ridge in these models melts and gets to the surface. But especially when you have different components, wouldn't it be expected, or would there be a role in the fact that some components may be more fertile than others, and therefore you may see the yellow more than the green, or something like that?
Right.
Especially these days, there are models of extraction at ridges which see channels being initiated where you have heterogeneities.
Right.
With, do we really sample all of those dots?
Probably we don't. I mean, the sampling is going to really depend, as you said, on the very fine scale behavior of melting, melt extraction, and so on. So we almost certainly are not perfectly sampling the upper mantle. There will be some mixing going on in the magmatic extraction processes as well. So that presumably is going to some extent smooth that out a little bit, but it won't, but if you leave behind some stuff that's never sampled, that's, a bit of a problem.
I just wanted to note and follow up on the comments about the thermal evolution of the Earth, and just, we're again in a situation where, as Louise said, we don't really have good rules for how to abstract, say, mixing efficiency and mass transport across the 660 as a function of Rayleigh number, right? Because we still don't really understand how slabs make it through the 660, for example. That said, folks like Takashi Nakagawa and Paul Tackley have presented models that provide a thermal evolution of the Earth for 4 billion years with continents and maybe even in 3D spherical geometries that do have a consistent evolution and that do provide, the synthetic data that can be queried. So it's not like people haven't done that, and I think there are aspects of these models that are quite robust that we can trust and others that are more debated.
I really want to ask a question about your last point in your summary. Is the Earth's mantle getting more or less homogeneous over time, and do we know?
We probably don't know, but but what I imagine is that we have these lower mantle blobs that have preserved heterogeneity for a long time, but we do see some evidence of that at the surface, which means they're being sampled, which means to some extent they're being eroded away. And what the time scale for that erosion is, we don't know. We know that they've lasted perhaps 4.5 billion years, but we don't know how long after that they will last. So that's still kind of an open question, I would say. But that in itself is going to gradually erode away the heterogeneity, so that if the Earth were to continue, going, as it continues going, we would expect that to basically get homogenized in with the rest of the mantle eventually. However, that's countered by the cooling. So the relative time.
That's only one part of Earth's heterogeneity. There's the melting part as well.
Yeah.
So
All
making plates creates heterogeneity.
Yes.
Probably faster than you destroy it.
Yeah. I mean, if we started with a magma ocean, right, you would expect you started relatively homogeneous, at least layered. And we're creating more heterogeneity now.
Right. You may be creating more. Well, certainly, the continents also are, are a heterogeneity themselves, right? They are a pocket of heterogeneity. So it depends on the extent of the magma ocean too, right?
One last question.
Yeah.
I just wanted to make a comment. So to Bill's point about the MORBs, you can see this in plots when you're looking in detail at the isotopes, but you actually had the Agronier paper up about the mid-ocean ridge to mid-Atlantic ridge. So when you do an actual spectral analysis on those data points, it's been done there. That's the best data set. But if you do it for the EPR or for other places, basically you come up with the same sort of idea that there is a peak on the scale of ocean basins roughly in this data. And then there's the smaller scale stuff. And that doesn't seem to really come out above significance too much. That's mostly hotspot related probably. But this data, without even having to squint at the XY plots, if you just make spectra of these things, you get a peak around, I think it's around 1,000 kilometers or several thousand kilometers even, usually.
Thank you, Louise.
All right, thanks.